So as Sean mentioned, I'll be talking about how we can make models of state-level decision-making and understanding the motivations for countries to pursue nuclear weapons in order to make regional models that assess the risk of proliferation. So in order to understand the question that we're trying to answer in this research is, why do states choose to proliferate? And the ultimate goal is that if we can understand why states proliferate, then that means that hopefully we can come up with policies and ideas to change those motivations and change the future of what nuclear proliferation may look like in the world. So what we need to understand first when we're looking at this is that states typically believe in our current status quo, that it's in their security interest to develop weapons capability. And this may be explicit nuclear weapons capability, but more often they're interested in having latent capability, which means that states often say that they're pursuing nuclear technology for energy purposes, and then later they have the ability to convert that into a weapons technology. So what we hope to do with our research is try to get at the fundamental motivations that are underpinning this belief that they're more secure when they have this capability so that we can change it. Now today I'll start by talking about the tool that I'm using to develop this model, which is called Cyclists, and how I'm using a unique capability in Cyclists that allows me to model the interactions between different actors in the simulation. Then I will introduce the model that I've built, which is a regional proliferation model. And then finally, I'll highlight some scenarios that we're hoping to apply the model to look at different policy proposals that may hopefully eventually change countries' proliferation motivations. So you may have heard about cyclists in other contexts through the CVT, and typically when we've talked about cyclists before, we've been looking at some of its applications for more traditional fuel cycle dynamics and tracking material flow. But what I'm doing with this research is actually something very different, and I'm not looking at material flow so much at all. I'm actually using a feature of cyclists, which is that it's an agent-based system. And this allows me to customize the behavior of each actor in my simulation and allow them to interact. So the feature of agent-based software is that every agent in the fuel cycle has its own decision-making logic. And that enables each agent to choose not only what kind of material or quantities they want to trade, but also who they want to trade with. The other main feature of Cyclists that's really useful in this research is something called the Region Institution Facility Hierarchy. In Cyclists, we have the ability to define these manager agents that represent how different sort of higher level non-facility actors can be involved. So here I have a drawing, just a little cartoon of what a region institution based simulation might look like. And it actually is showing a simplified version of the fuel cycles for Ukraine, Russia, and Iran. So in blue on the left, I have the fuel cycle for Ukraine, and it looks pretty traditional. It's got a mine on the top. The material from the mine actually goes to the red, which is Russia's fuel fabrication facility. So Ukraine and Russia are interacting. And then the rest of Ukraine's fuel cycle, the reactors and the fuel waste, stay within Ukraine. And on the other side in green, I have Iran's fuel cycle, which is currently under the JCPOA very simple. It is just a reactor. And under the agreement, Iran has to get all of its material from Russia, and then it has to send all of its used material back to Russia. And so under this scenario, Russia is sort of the country in the middle, and Russia can trade with Ukraine, and Russia can trade with Iran, but Iran and Ukraine are not permitted to engage in any flow of nuclear material between them. And so Cyclists allows us to model something like this by creating individual regions that represent governments and allows us to model things like trade agreements and sanctions so that we can force these behavioral decision-making processes into the simulation. Now I'm going to introduce to you what this actual model that I've created is and how we're looking at proliferation risk. I'm working with a political science graduate student at the University of Wisconsin to identify the motivating factors that go into the decision-making process when the state decides whether or not to proliferate. And using existing literature, we've identified a set of 8 different factors that we believe contribute to this motivation. Now here I've listed them out. On the right you can see a funnel plot that shows the relative importance of each one of these factors as we've ascribed to it. And on the left I've highlighted that these fall into 2 major categories. One is internal factors, and the other is external factors. So internal factors are things that affect the country internally. This may be economic factors, how much of their GDP is available for military spending. It may be political factors, what their governing structure looks like, if they're authoritarian or democratic. And it can also include technical factors like, do they already have sensitive dual-use technologies such as enrichment and reprocessing, or do they have their own uranium reserves, or do they need to buy that from another country? In addition to these internal factors, we also have a couple of external factors. And the external factors are the factors for which if you just look at a single country by itself, you're not going to get all the information you need. So the primary example of this is regional stability and conflict. If there are 2 countries, multiple countries in a region, you need to know not only what's going on within country A, but you also need to know how country B affects country A. And so we've folded these external factors into our model as well. And the last external factor I want to highlight today is what we're calling the scientific network. Now, if you're familiar with how Pakistan got its nuclear weapon, they basically had one man, A.Q. Khan, who was able to develop a network of connections with experts from all over the nuclear fuel cycle, whether they be scientists, engineers, industry partners, and they were able to actually produce their entire weapons program without starting at sort of the traditional, let's get the energy technology first. And so one of the major concerns about future proliferation scenarios is this concept of networking with people from other countries who have the information that you need in order to build a weapon. So on the right, as I said, I have this funnel plot for the pursuit equation, and this is the equation that we've defined in our simulation that estimates the likelihood that a country will proliferate. And each one of the numbers going down the right-hand side shows the relative weighting of these factors. So we combine these factors just in a linear weighted equation to come up with our total likelihood of pursuit. Now, in order to gain some confidence in this model, because it's a pretty not technical type of model, we have been examining the relationship with historical data. So we've taken the set of all the countries that have at some point proliferated, considered proliferating, or have significant nuclear technical capabilities that may enable it to proliferate in the future. And we've applied our model to make this calculation. So for each country that you see on the plot here, we have calculated what its pursuit score looked like at the time that it made a proliferation decision. And for the countries that have never chosen to proliferate, we've looked at the modern day numbers. So you can see here that dark red is highly likely to proliferate, and light red is unlikely to proliferate. And the countries that are shown in beige are countries for which we didn't run the analysis. So just to give the ballpark estimate, we see that countries like Russia were highly motivated to proliferate at the time that they did so. And this is consistent with, our model is predicting things consistently with historical data. And countries like Australia are showing up in very light red. Obviously they haven't actually tried to proliferate, so that's good that our model is consistent. But of course what we want to do is not actually look at historical data, but we want to have a forward-looking model. And so we need to look at not just benchmarking it against one static time point, but also thinking about how these factors may evolve over time. So there are a lot of contributing things that could happen that can change a country's motivations. These factors can include things like political upheaval, whether or not there was a military coup. They could include things like economic growth or disruptions. They can include things like whether or not their neighbor becomes proliferant. So if my neighbor decides to develop their own nuclear weapon, that may make me feel much less safe if they're a neighbor that I'm in conflict with, or they may make me feel more safe if they're one of my allies. And then finally, new treaties and security assurances and other policy tools may also influence these motivations. Now, how do we do this with our traditional nuclear fuel cycle simulator, which is Cyclists? Now, in order to do this, I have created 2 custom archetypes for our Cyclists fuel cycle simulator, and these are managing agents. And I call them the state institution and the interaction region. So the state institution is a manager that represents the actual country at some level. And its role is to track the time evolution of each one of those factors that go into the pursuit equation and to calculate for a given time step what each factor is and how they go into that equation that determines the likelihood of proliferation. Then once that calculation is done and we determine the likelihood that a state will proliferate on that time step, we have to convert it into an actual decision. If the state has a 10% chance of pursuing, are we at the time step where that 10% happens or not? Now, the other custom archetype I've created is the interaction region. This is an overseer manager, and so it basically knows what's happening everywhere in the simulation. And this is done so that we can track these external factors that require coordination between states. So this interaction region keeps track of if country A is in conflict with country B, then country B also knows it's in conflict with country A. And it shares that information with each of the individual states so that they can make their calculations about whether or not they're going to pursue on a specific time step. Now, most of what we've done with this model so far has just been testing it out to make sure that the way we've implemented it is consistent with our expectations. So this is a simple example of one of our tests. So in this test example, I've created a one-state scenario. So I look at the course of history over 100 years for a single state, not thinking at all, for simplicity's sake, about those external factors, just looking at the internal factors. And I give the state an initial score of a 5 on a score of 1 to 10 for that pursuit equation. I give them a score of a 5. And the 5 that I've chosen for this example is because in historical data we see that a score of 5 on our scale is about where we see countries switching over from not choosing to pursue weapons to going through that process. So I run the simulation over 100 time steps and I see whether or not the state has decided to pursue by the end of that simulation. And then to make it more useful, I actually do a statistical study and run the same initial conditions over 1,000 simulations. So I can see in a statistical sense what's going on with our simulation. So here I have a plot of, it's just a histogram showing the fraction of proliferation events that occur over the course of all of those 1,000 simulations and at what time point in the simulation they occur. So as we would expect to see, we have an exponential decay. So more at a pursuit equation value of 5, we have more than 50% of our simulations result in a proliferation event within the first 10 years. Now this is where we're currently working to try and estimate, to try and use historical data and understand realistically how much time it takes once a country makes a decision to pursue a weapon, how long it takes them to actually get to developing it, and whether there are, and what factors influence that aspect as well. So that's continuing work in this area. Now I've also done this at the other two extreme for our equation. Our equation is fundamentally has a minimum at 0 and it has a maximum at 10 because of the way we've defined it. So I would show you the 0 and 10 cases, but they're pretty boring. For the 0 case, you see no proliferation in the entire simulation for most of the time, and for the 10 case, pretty much all the countries proliferate right away. So this is the more interesting example. So that summarizes what we've done so far with our model, and what we're starting to work toward now is actually looking at a policy proposal. So today I'm just going to outline the first policy proposal that we would like to apply our model to, and that is multilateralism. So there's under the status quo, every state that has signed on the Nonproliferation Treaty has the right to produce their own enrichment facilities and to develop that technology. And because this is a dual-use technology, this is not really what we want from a policy perspective and in terms of trying to reduce nuclear proliferation. So a multilateral paradigm has been proposed whereby instead of having every state develop its own enrichment technology, we get groups of states together and they develop multinational enrichment facilities, where in that group of states you have a country that already knows how to produce enriched uranium, and they're the ones who control the technical operations of the facility. And then the other countries involved are going to be countries that don't have that technology, and they are able to still participate in the facility, run the day-to-day operations, get the economic benefits that may come out of enriching uranium, and also have some fuel supply assurances. But they don't have access to the technical parts of the facility. Now, the major advantage to this type of scenario is that we reduce the proliferation of enrichment technology. But the disadvantage and the drawback that people argue with is that this may actually increase that scientific network. By taking a bunch of scientists from countries that don't have enrichment and putting them in an enrichment facility with scientists who know how the enrichment facility works, you may be developing those connections. And so it's not clear a priori that this would actually reduce proliferation risk. So our plan is to take our proliferation model and make a model of these two scenarios. Make a model of the status quo and look at a region. See what happens in the region if any state that's in it can proliferate over the course of 100 years or can develop enrichment technology. And then we will also make a second scenario that has the same initial conditions as the status quo, but is using this multilateral enrichment paradigm where we're not spreading the enrichment technology. And then we want to run each of these scenarios over 100 years and change and do sets of different conditions. See what happens in these scenarios if we have a military coup. What happens if you have a group of democratic countries? What happens if you have economic disruption? And try to tease out under what conditions is proliferation risk decreased in a multilateral paradigm, and under what conditions is it not going to be helpful. So that's our plan for the upcoming year. Now, the last thing I want to mention is that our model is indicative, it's not predictive. I'm not making any claims that you can take my model and look at the world for the next 5 years and predict which country is going to be the next country to proliferate. It's really about looking at the relative risk between different types of scenarios and trying to understand how we can develop policies to reduce that risk. So with that, I'll wrap up. Today, I have introduced how we can use Cyclists for non-proliferation using its agent-based framework. And we do this to facilitate the modeling of the behavior of actors in the simulation. We've developed a regional proliferation model that captures the motivations of countries to pursue weapons. And we plan to apply this model to scenarios such as multilateral enrichment that may have the potential to change the motivations and policies on the world scale going forward. So with that, I'll ask for questions. Thank you.
But we modify this concept quite a bit. So instead of having a regular SAR ADC, we use a SAR ADC that has specific ranges, okay, very coarse ranges. So that